morning, everyone. Thank you for sitting here to the very last talk of this nice conference. And I would like to thank the organizer for allowing me to talk about this work. So today I talk about this Majorana leaking on quantum dot and some game that the Majorana play with Kondo effect in the quantum dot. So I'm from this Federal University of Uberlândia. It's quite far from here. It's probably it's not as nice like this because we don't have a sea and a nice place like this. So anyway, once again, I would like to thank the organizer because it's our pleasure to come a very nice place and conference. So I have to thank my collaborator in this work, who is Carlos, who is right there, Petiado, Gregorio, Tijerina, and Ceridone. Part of this work, you have interaction. So people who likes this interacting systems, I hope we enjoy. So for the first part, there is no interaction. So I hope I can make it clear for you. So here, since we're talking Majorana fermion, I just show picture here. Here is, for example, a proposal in which you can have superconductor, S-wave superconductor in proximity with quantum wire with spin orbit interaction. And what we see, we have applied magnetic field. You can drive this system into its topological phase, and then you find edge Majorana mode here, or end the Majorana mode if you wish. First experiment, when it worked, it was argued that Majorana was seen and was observed. The signature would be this zero energy peak in the conductance. Another experiment was proposed and actually measured in a ferromagnetic chain on top of superconductor. So this essentially the first or important motivation for study Majorana theoretically and experimentally. There are many others. Maybe your favorite is not here. I apologize. But the simplest way from the theoretical point of view, the simplest way to see Majorana is through the Kitaev model. I think everyone is familiar with. So let's show it once again. Here we have the famous spinless Kitaev chain. We have chemical potential with the on-site energy of the sites of the chain. You have the hopping, which just a T is a overlap matrix, and have the pairing potential. This is a P-wave pairing potential. This is essentially the effective model you can get from the entire system with spin orb in the higher topological superconductivity induced and magnetic field. So, how do you can get Majorana here? And essentially, if you define new operators, in the other way, if you write your firm in terms of new Majorana operators, so then in replacing the Hamiltonian, you will get this Hamiltonian in terms of these new operators, which are these Majorana operators. So then you write the chain, in a sense you just splitting the single fermion side, you split in terms of Majorana A and B. So you see they are out coupled with each other. And the blue correspond to mu, and this pink is T plus delta, and the green is T minus delta. You can immediately see that if T equals to delta, for example, the green line is not there, and if you take mu equals to 0, also the blue line is not there. So what you have is this chain. If the chain is infinite or periodical boundary conditional, so each Majorana has a neighbor So you can hold their hands. So this situation, the system, the chain is gapped. On the other hand, if you cut the system, so there is no neighbor here, so you see this poor Majorana becomes alone. So this is essentially the Majorana edge or end state in the wire. So, since I'll talk about Kondo effect, I have to explain at least in one slide what I'm talk about this many-body effect. Suppose you have a quantum dot, for example, an impurity or magnetic impurity, for example. Here is, I'm thinking about a quantum dot in which on one level you can have one electron, and this electron is coupled to a Fermi C, for example. So because of this electron interacting, so the second electron cannot come spin, the opposite spin. So this fainting arrow here represents an electron that possibly can go there, but had to pay an extra energy. So if you put the Fermi level right here, you cannot be occupied by two electrons. But virtual process can happen, and then what you see is the effectively singlet formed by the localized electron and the conduction band. So what is the signature here is this peak. This is a dense substate, local dense substate at the dot side as a function of energy. And here I'm moving this the level. You see that here, if when the level is above the Fermi level, you see there is no zero peak. But now, when it becomes below, you see a zero peak that spinned essentially there for a quite long range of Vg, which is marked by this gray arrow. So, so these are essentially these two modes. Let's say you can call here a Condo mode or Condo virtual bound state, if you wish. So this, what I'm showing now is the interplay between these two bound states. So now I come back to the Majorana, but now it's a more complicated system in which you have a theta heavy chain here with the green circles. We have all the ingredients and T and delta and everything. So these, at the end of this theta heavy chain, a couple on a quantum dot. So here, still, I will not put interaction in the dot yet. So what we have seen actually is that when you calculate, for example, conductance here, you see some kind of a pinning of the zero energy peak. It's a differential conductance that actually could be measured. You calculate from two normal leads here. So if you look, for example, at the dense substate of the quantum dot or the edge or the end of the chain here, you see the following picture. Here I plot, for example, the dense substate of the dot and the dense substate at the end of the chain. For different coupling between the dot and the chain. You see, for example, for zero, for sure you have the single particle level of the quantum dot, because the energy of the dot is just set at minus 5 gamma left, where gamma is gamma lead. Where it's gamma lead is essentially the broadening of the quantum dot because it's coupled to a continuum. So when you increase T naught, you see that zero peak appears there. You keep increasing the zero peak, remains there, but just get a little bit fat. And small satellite peak you can see here too. But essentially, this curve are shifted just for clarity. But the height of this peak is the same, regardless the value of this T naught above certain characteristic value. So here, for example, I'm plotting both. Here, actually, I'm plotting the dense substate of the chain. You see that when increase, the coupling actually decreases and eventually vanished. Now here, essentially, the denser state at 0 of the end of the chain, which is called row 1, and the row dot, that increases. Up to here, it doesn't depend anymore on the coupling T naught. So what we can see here, actually, the Majorana is disappearing from the end of the edge and showing up the dot. So this is what we call leaking. So, okay, then you think of you think a little bit and wait a minute. This is actually because the quantum dot actually represent, in a sense, an additional side of the chain, and then the Majorana has to appear at the end. So that's why it appears here. So in this sense, you can think that the quantum dot is not a weak perturbation of the system, because they essentially move the Majorana from where it was without a dot. So now, if you look at denser state a little bit more careful, now here I have the denser state with the color map, and I have the energy of the dot, and essentially the energy of the dot. This is its energy, and here is the dot level position. So you see here, there is a peak. You see the scale from 0 to 1, because it's normalized by pi gamma, which pi gammas give you the correct height of the Friedel, which is related to the Friedel sum rule. And if you see, you can see here that this peak remains thin, regardless the sign of this the dot level position. Other than this, you see, it's not only the dot, the Majorana not only leaks into the dot, but remain pinned to 0, which also, you say, wait, it makes sense because it cannot be disturbed by gate voltage, for instance, right? So, but this, if you see, this is a very interesting, because you can use this to probe basically Majorana in the system, not in the chain, but in the system, let's say. Because now I'm arguing that the Majorana is in the dot. So here I have the level position of the dot. I'm just plotting along this line, and I have the conductance, which in the symmetric coupling regime is proportional to the denser state of the dot. You see here, this for different value of mu, which can be driven from the topological phase or the trivial into the trivial phase of the Kitaev chain. For example, if mu is smaller than t, you are in the topological phase. But if mu is above t, so then you are in the trivial. So here I have 3 plots. Here I have 2 curves, which the Majorana, the dot is coupled. Actually, all that is coupled by 10 gamma, but in these 2 curves, you are in the topological phase. You see this almost flat plateau of the conductance. When you go to the trivial phase here, you see that the peak go almost to 1, and this is no longer a plateau. I have a very well-defined width associated with gamma. And this green line here, when you set mu and delta to 0, so the Kitaev chain becomes normal lead, normal wire. So this is you see this plateau is not a plateau, and has not well-defined height. It depends a lot of gamma and this decoupling T and so on. So in this sense, you have peaks for the Majorana and from the Condo effect. I didn't calculate Condo yet, but you can now compare, for example, the features, because in Majorana case, what we have seen is that I have a 0 peak because of this. It means that I have a zero peak even if the dot is empty. And, or full in this case. In the Condo, as I show in this cartoon, you see that, the little movie, you see that the Condo peaks just show up when the dot has one electron, because you need the magnetic field in the dot. So you can, this is just a sketch of the Condo behavior. But now, this actually was argued to be seen, this leaking in this experiment very recently. But here the conductance or the transport were measured in this direction, where here in the other direction, in the transverse direction, we say. The result could be different, interpretation could be different in sense. So now let's go to interacting dot, because now we want to put the Kondo and Majorana together. Some people say that we don't want Kondo in the system, but here I'm kind of acting like the politicians. If I can make things more complicated, why not? So let's do it. So here I have the full model. In order to calculate Kondo, to address Kondo effect, I need to have two spin, because the Kondo effect, essentially the basic ingredient is magnetic moment, localized magnetic moment, and time reversal symmetry. It's not really broken by time reversal symmetry breaking. So it cannot destroy immediately. There is a crossover, but in principle, a spin has to be able to fluctuate in this sense. Small magnetic field, you still have Kondo, even though the time reversal is broken. So here is the full model in the sense you have a tight bind chain with a Zeeman effect and spin-orb coupling, and so this, and also we have not shown here. We have here we have the induced superconductivity. It's actually S-wave superconductivity. And here I miss the spin sign here. So, and the new ingredient here is that in the Kondo dot I have the Coulomb interaction, which is essential for the Kondo effect. So how do we do this? The first try actually is to calculate the high temperature regime. We calculate using Green's function, this decimation procedure or iterative Green's function, if you wish. Many names. It's in a sense you can do the same we did actually for the Kitaev chain, but here it's more complicated because there is no exact solution anymore. So the first approach is actually to make some high temperature approximation, which called Haber-1 approximation. We know that we cannot describe Kondo, but let's see how the Coulomb location can change this thing. Here I plot the denser state of the dot for both spin up and down. If you see, in this case here, I have the non-interacting regime. So just put U equal to 0, and here have interacting case. The panels means actually stand for the dot, the dot of level dot at 0, negative, or positive. So in here the dot is empty. Here the dot has 1 electron, and here the dot 0. Actually has 2 electrons, but I no interacting. Here you have 1 electron only. So you see this. Forget a little. Forget for a while the blue line. So let's look at the black one, which corresponds to spin up. You see that essentially it's not really changed. You can see anything at 0, because the magnetic field or the Zeeman is splitting in such a way that the dot couple only to the one of the Majorana couple only on a spin species of the dot. If you change the sign of VZ, it couple to the other, but the result is essentially the same. So here, because they only spin down on the dot couples to the Majorana, you see that when you look at the denser state for spin down, you have a 3 peak, and this characteristic 1/2 peak here. So if you put the level of the dot below the FEM level, you see that the zero energy, the single particle peak here, but you have this additional peak over there. It's not seen in the black curve. Similarly, if you put there, you see this zero peak here. So essentially, the second approach is the same, gives essentially the same result as the Kitaev model. Now, the interacting case, you see the zero peak still there, you see, for when the dot's empty. Here you see if you can, it's a little bit different, but as far as you look at the close to energy to zero, here is essentially the same because when the dot is empty, Coulomb repulsion can make any difference essentially, at least for low energy. But now, when you put one electron in the dot, you see that the second electron, this is the denser state, is essentially the Haber band, if you wish. It appeared there. But an additional peak, like it's kind of reminiscent of this, appear there. And when the dot is completely empty here, it's the same here. You don't have, probably to have one electron, that's why this have this little band here. So, and interesting to see that this peak here is a little bit shifted. This was a zero, and this was shifted. So then I imagine also then the interaction can disturb the spinning. But actually, I have to tell you that this is an artifact of this Haber-1 approximation. It's not the right way to see it is actually to go to a numerical group calculation, what we did, I will show in a minute. But now, I want to apply, for now, you can imagine that the dot, the Zeeman splitting of the dot up to now was pretty much irrelevant. We didn't take into account. But if you include the Zeeman splitting in the dot, you see that you recover the non-interacting case even if the dot have one electron. Because Zeeman effect is big enough, so the second electron prevented not because of the Coulomb repulsion, but because of you have to pay Zeeman energy. So now, if you want to go to do non-perturbative calculation like Kondo effect requires, you have to do some numerical renormalization group or any other approach if you want. Here we apply now the numerical normalization group. So the problem is that in the full model, it's hard to apply this procedure because it itself is computationally very heavy, the NRD calculations. So we went to an effective low energy model. So this model, we assume that the wire is already in the topological regime. So only from this chain, or Kitaev chain if you wish, only this Majorana is there. So the only one that coupled to the dot. In principle, there is actually always there is another Majorana somewhere in the infinite. So they are maybe coupled if the wire is not that big. So, but this we just neglect, assuming that the wire is big enough. So this Majorana coupled to the dot, we spin down of the dot. So here actually we compare. Is now it's the same plot actually. We compare the result from the effective model and the full model. We see that actually the blue line lies precisely on top, or at least good deal. We find a good deal agreement between, especially at energy close to zero, which is more important for the Condo effect. So actually, why you need that? Because actually this coupling here is somehow depends on all it's an effective coupling that depends on all these parameters of the Kitaev chain, or if you wish, the parameter of the full wire model. So in a sense, you can always play with this lambda in such that you find the agreement. That's how we did. So, but still have another complication because there are some technicalities when you apply numerical normalization group because you have to diagonalize a growing chain. If you have to map to the map this system into a Wilson chain, which essentially you are adding sites, and the Hilbert space increase very fast. So you need to adopt some good quantum numbers. So you write Hamiltonian and diagonal blocks. But here the problem is that this term does not conserve particles. So Q is not the total charge of the chain, of the Wilson chain, is not a good quantum number. So, but and also this Wilson approach, you have to define Fock space. But this guy doesn't form a Fock space. So you have to bring back the other Majorana, which the only one is somewhere in the other side, and then you form this complex fermion. So then you have a Fock space well defined. But you see this number of electron spin-up is conserved. It's great, but it's not conserved. It's bad. But you can find this quantity which is conserved. It has to do with the parity, because the superconductivity changed the number of electrons by 2. So doing this, if you implement this in your numerical calculation, and then now we plot the same quantities, the dense substate of the dot for spin up and down. You see that we have this for u equals to 0. You see, you have this peak over there. When the dot is empty, it's right there. Nothing essentially happened here. There's a little bit shifty here. When the dot have 1 electron, you see this Condo peak. You see that goes to 1. This is the Condo peak for spin up. If you look at the spin down, for instance, you see for u equals to 0, this peak, which is Majorana peak, go to half. And if you look in the interacting case, you have one peak which is on a half. So is it Condo peak or Majorana? Seems to be Majorana because it goes to 1/2. But if you compare the shape, it looks like Condo. So it's somehow the Majorana is playing with Condo. So actually, we see that this Majorana coexists. We can say that you have Majorana and Condo feature together. So there is, if you do some Schrieffer-Wolfer transformation, the Anderson-like model, you can find actually there is a magnetic field because the dot couples, only the spin down of the dot couples to the Majorana, so you can have some kind of effective magnetic field that somehow distort the dense substate. So here you can define 2 quantities. The Condo temperature, which actually should be a little bit down here. I don't know how it's moved. But half width at half maximum here, you can define the Condo temperature. And here you can define, you see, should be here. I guess I moved this. This half width of this peak is, we call it Tm, which is some temperature associated to the Majorana 0 energy peak. So now, now going back to the magnetic field in the dot, for example, if there is no magnetic field in the dot, have this feature. If you consider magnetic field in the dot, you see essentially the 0 energy, but the non-interacting case, you compare with this, you see, it's essentially the same plot. So magnetic field kills Condo effect and you recover the Majorana. So in this sense, somehow increase the effect of this, the Zimmer effect in the dot. You can just kill one of those and keep the other. Okay, I think the last, almost the last plot, one bit more. I'm in the last speaker, so I have more than 5 minutes. Thanks. So, so a little bit more subtle to calculate this TM energy, because you see, here is the dense of state for spin down for different couplings. If the coupling is very tiny, you see the peak goes to 1, which corresponds to the Condo peak, but there is a dip, you see. So somehow it's quite hard, because in some case here, for example, there is no dip, essentially. You cannot define a dip. So you can define here as a width. So here you can, this is a plot of this, this is actually a logarithm plot of this same dense of state. You can define here, for example, in this region, you can define width, Tm as the width of the peak. And here is the width of the dip that right in the middle. So in a sense, when this, in this case here, you can say that you are in the Majorana dominated regime, and here you are in the Kondo dominated regime. So now we plot these two quantities, dk and the Tm, as a function of lambda, which is the coupling between the dot and the Majorana mode. You see that this is the Kondo temperature, which is calculated from the width of the spin-up peak. You see that goes smoothly and stops somewhere when lambda is 0. But it's a completely different behavior when you go to Tm, because it goes quite smoothly, but it doesn't go like Condo temperature, a little bit above, but then it goes to 0. Because when lambda is 0, there is no dip here, so it's like the dip goes to 0. And somewhere in between is hard, because these two lines are right close to each other. You cannot really define a peak or a dip. So, what is the nature of this? So you can plot, for example, scale. Right? You know that that the Condo effect has some very defined energy scale with decay. Any quantity, for example, temperature or magnetic field, you apply scales with decay. So here is, we are plotting the VZ of the dot. It's a Zeeman splitting of the dot, and have the conductance. You see that the curve for different lambda, with lambda is the coupling between the dot again, the coupling between the dot and the Majorana mode. You see the curves are completely separate, have the same behavior essentially, but they are shifted. But if you scale with TK, and then you find a very nice universal behavior, which tells us that the universality of the conductance of the Condo effect is there. Okay, you can go further and calculate this residual entropy, because you can stop and step back and say, look, you have a half peak, half height peak. But you know that the Condo is, the original, traditional Condo is Fermi-liquid. So is this non-Fermi liquid? Actually, there is some characteristic non-Fermi liquid behavior, which is this residual of entropy, which essentially half particle that's there, essentially. I'll leave here my acknowledgement. Thank you.
Okay, we have some time for questions. Otherwise, I might ask the question, in the Kondo effect.